Today we are going to deal with catalog of functions. Recall from our previous lecture that a piecewise function is where we split the domain to make two or more functions. Consider this example. F of x equals x plus 2 when x is less than or equal to 1, and f of x is equal to x square when x is greater than 1. If we look at the graph of the function, the graph looks somewhat like this. So as x plus 2 when x is less than or equal to 1. So this is the graph of x plus 2 when x is less than or equal to 1, while x square when x is greater than 1. So we have this, and mind that we have a hole in the graph here. Looking at the domain of the function from the graph, it is clear that it is all real values, because as x is greater than 1, everything here gets covered, while when x is less than or equal to 1, everything from this side gets covered. So my domain is all real numbers. However, my range is from 0 to infinity, that is all positive real numbers. Clearly you can see that the graph never exceeds the x-axis. This area is never covered by the graph. So it's pretty clear that how the graph is only on the positive y-axis. So the range is 0, infinity, 0 closed. We now move on to symmetry of a function. Let f be a function from R to R. You call these kind of functions as real valued function. Or a real valued function is a function where f of x is a real number. So we have a real valued function f, then f is said to be even if it satisfies f of minus x equals f of x for every real number x, and x is said to be odd if f of x is equal to negative f of x for every real number x. Let's look at some examples to understand this. First one is f of x equals x squared. If we look at the definition of even and odd, the first thing we need to do is calculate f of minus x. So let's look at what is f of minus x. So f of minus x equals minus x the squared. Minus x the squared is x squared, but x squared equals f of x. So from here, you shall see that f of minus x is equal to f of x, which means the function is even. So we color even with blue, while we color odd with red. So this function is even. Now we look at f of x equals sine of x. Again, we do the same thing. We find f of minus x. F of minus x is sine of minus x. We know sine of minus x equals minus sine x, which is equal to negative f of x. This shows that sine x is odd. If we go on checking all these functions in a similar fashion, we find out the following. Cos of x is an even function. Tan of x is an odd function. X cube is an odd function. Now we come up to this function. This is a very important piecewise function. This is known as the modulus function. To know more about this function, please refer to my previous lecture video where we talk about functions and piecewise functions. A modulus function is a piecewise function of the form x when x is greater than or equal to 0 and negative x when x is less than 0. So what we do here is first we look at f of minus x. F of minus x is absolute value of minus x. Absolute value of minus x is x. So this is equals f of x. That is x which is equals absolute value of x which is equals f of x. So clearly f of minus x is equal to f of x. So modulus function is again an even function. In this manner, you can check more functions yourself. However, please note one thing, that not every function can be categorized under even and odd. Meaning, there could be a function which is neither even nor odd. One example where I can show that a function is neither even nor odd is of this form. Consider f of x equals x square plus x plus 1. Using the similar method on the top, we calculate f of negative x. F of negative x equals minus x squared plus minus x plus 1, which is equals x squared minus x plus 1. This is neither equals f of x, neither equals negative f of x. If you want, you can calculate negative f of x. Negative f of x will give me minus x squared minus x minus 1. So here you see that this function is neither even nor odd. Now we come to another concept known as linear functions. A function whose graph is a straight line is known as a linear function. Or algebraically, a linear function is a function where f of ax plus by can be written as a times f of x plus b times f of y. We have two ways of writing a linear function. A linear function can be written in the form of slope and intercept. That is, y equals mx plus b. Where m is the slope while b is the y-intercept. Let's look at the following example to understand this more. We have an equation y equals 1 by 2 times x minus 3. What we do is we first plot points from x comma y on the Cartesian plane. We first put y0. So as y is 0, I have x equals 6. As x is 0, we have y is negative 3. As x is 1, we have as x is 1, we have y equals 5 over 2. So now let's plot these points on the graph, on the Cartesian plane. This is our Cartesian plane. You have the x-axis, you have the y-axis, we have the origin. So at y0, we have x equals 6. So we have 1, 2, 3, 4, 5, 6. This is 6, 0. So this is 1 point. Next is when x is 0, y is -3. So we have the point here. And when x is 1, y is 5/2. So x is 1, then y is 5/2, which is around 2.5. So 2.5 is somewhere here. So we shall have it somewhere. It's -2.5. I'm sorry. Should be -2.5. So -2.5 should be somewhere here. Here, yeah. Now we join the line. This is the equation of the line y equals half x minus 3. Next form comes the point and point form. That is, we are given 2 points and then we can find the equation of the line. Third type is point slope form, where you're given a point and a slope to find the function. One example of point-point form would be write an equation of a line passing from -1, 2 to -2, 5. We do the following. The formula is y minus y1 equals m times x minus x1, where m is y2 minus y1 divided by x2 minus x1. So our first job is to assign x1 y1 and x2 y2. We assign this as x1 y1 and this as x2 y2. Now let's construct the equation of the line. So we have y minus y1 is 2 equals m times x minus x1 is -1, which makes it +1. Now we calculate m. M is y2 minus y1 divided by x2 minus x1. So y2 is 5, y1 is 2, x2 is -2, x1 is -1. So x2 minus x1 would become -2 plus 1. So we have 3 divided by -1, which is -3. So y minus 2 equals -3 times x plus 1. Solving further, you'll have y minus 2 equals -3x minus 3. You have y equals -3x minus 1. This is the equation of the line. Using the previous method, you can plot this graph. I leave it as an exercise. We now move to a category of another important function known as the polynomials. A function p of x is called a polynomial if it can be written in the form of p of x equals an x raised to power n plus an minus 1 x raised to power n minus 1 plus similarly a2 x square plus a1x plus a0, where n is a non-negative integer, that is, n is always greater than or equal to 0. Now comes a0, a1, an minus 1 and an's, that is these terms. These terms are known as the coefficients of p of x, and these terms are always real numbers. Please note that the domain of a polynomial function is always negative infinity to infinity or all real numbers. First example is P1 of x. P1 of x is x squared plus x plus 1. Then we have another example for polynomial function, that is x power 4 plus 3x cubed plus 9x squared plus 11x plus 12. Then the third example is x raised to power 10 plus 2x power 9 plus 5x power 7 plus 3x squared plus 1. For a polynomial p of x equals an x raised to power n plus an minus 1 x raised to power n minus 1 plus dot 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 plus a1x plus a0, if my an is non-zero, then the degree of the polynomial is n. The degree of the polynomial determines the end behavior of the polynomial. I will talk about this more in the later section. We define a degree of a polynomial. Look at the highest power of x in p of x. The coefficient corresponding to the highest power f of x is my leading coefficient. Make sure that your highest power of x should have a non-zero coefficient, because you could always write something like this. If you have p of x equals x squared, I could always write p of x as 0 times x cubed plus 1 times x squared. Here, my coefficient, my highest power looks like x cubed, while my coefficient corresponding to it is 0. So this term is not there. So make sure that the non-zero coefficient corresponding to the highest power. So we look at the non-zero highest power of x is my leading coefficient. So clearly in this case, in p of x, my leading coefficient is 1. Let's come to these three examples and find out their leading coefficients and the degree of the polynomial. The first one is clearly a polynomial of degree 2 and the leading coefficient is 1. The second one is of degree 4 and the leading coefficient is again 1. The third one is again degree 10 while the leading coefficient is again 1. The next topic we come on is power function. A function of the form f of x equals x raised to power a, where a is a constant, is known as a power function. So as my a changes, my function shall change. I have three possibilities for a. A can be positive, a can be negative, while a can be a fraction. Let's look at all of these conditions one by one. Case 1, when a is equal to m, where m is a positive integer. That is the first case. The moment you plug in m as a positive integer, notice that f of x turns out to be a polynomial function. The first function, that is f of x equals x squared, gives me a parabola. The second function, x cubed, gives me something like this. The third function, x raised to power 4, gives me something like this. And so on. Next comes when a is equal to 1 over m, where m is a positive integer. This gives rise to functions like square root functions, like square root x, cube root of x, fourth root of x, etc. The first function, square root of x, the graph would look something like this. The second function, cube root of x, the graph would look something like this. Next comes the reciprocal function, that is when a is equal to -1. The moment a is equal to -1, I have 1 over minus x. The graph of 1 over minus x looks something like this. You have two rectangular hyperbolas which turn from the point 1, 1 and achieve infinity as you go on increasing and decreasing x. Next comes rational functions. A rational function is of the form px over qx, where px and qx are functions, are some functions, and qx is non-zero. Consider this example, f of x equals x square plus 1 divided by x minus 2. Clearly, we have domain issues here. For f of x to be well defined, we want x minus 2 should never be equal to 0, which implies x should never be equal to minus 2. Therefore, domain of f should be all real numbers minus 2 or minus infinity comma 2 union 2 comma infinity, open on both sides. Next comes a very important section of functions known as the trigonometric functions. The trigonometric functions are usually functions defined on an interval or a function defined on r to r, where this r we usually deal with radians. So we look at the graph of all the 6 functions. The first one is the sine function. The sine function has a has the domain all real numbers. The domain is all real numbers, while the range is -1 comma 1. So we plot the graph. So we make +1, we make -1, and now we make the following. At sine pi by 2, the graph attains +1. At pi, graph goes to 0. At 3 pi by 2, my graph goes to -1, and so on. Sine, as you can see, is an alternating function. Similarly, on -pi by 2, sine attains -1. On minus pi, sine goes to 0. While on +3 pi by 2, sine attains +1. -3 pi by 2, sine attains +1. Now we plot it. The graph would look something like this. Something like this. This is an alternating function, always alternating between -1 and +1. From the graph, you have domain is all real numbers, while range is -1, 1. Similarly, we can plot cos of x. The domain of cos of x is all positive numbers, while the range is again from -1 to +1. Cos of x would look something like this. The graph attains its peaks at points 0, negative peak at pi, again a positive peak at 2 pi. It attains 0 at pi by 2, 3 pi by 2, and so on. Observe that the graph can be reflected through the y-axis and it's almost symmetrical by the y-axis. So this is minus pi by 2, this is minus pi, this is minus 3 pi by 2, and so on. So the graph again, as usual, alternates between 1 and minus 1. So the domain of this graph is all real numbers, while the range is minus 1, comma 1. Next comes the tangent function. For the tangent function, we do the following. We have tan pi by 2 is not defined. So what we do first is we construct dotted lines at odd multiples of pi by 2. That is at pi by 2, 3 pi by 2, and so on. This is pi by 2, this is 3 pi by 2, this is minus pi by 2, and this is 0. As x increases, tan increases, and the moment it goes towards pi by 2, it starts achieving infinity. As x decreases, tan goes towards negative infinity. And tan does this everywhere. This is pi. This is how the function of tan looks like. The domain of tan of x is clearly all real numbers minus the points of the form 2n plus 1 pi by 2, where n belongs to natural numbers. While the range of the function is minus infinity, comma infinity. This is clear from the graph as you look at it. The next kind of function is cotangent. Looks like tangent, just flipped the other way. So this is the cotangent function. In case of cotangent function, we have that cotangent functions are not defined at n pi's. So for instance, it is not defined at 0, not defined at pi, 2 pi, etc. So we draw dotted lines at these points where cotangent is not defined. We look at the cotangent function. So, as I said, the cotangent function is not defined at n pi's. So, we shall draw the graph of this function. In the graph of this function, the following happens. As x is decreasing, the graph goes to positive infinity. At pi by 2, it crosses the x-axis and goes towards negative infinity as it approaches pi. Similarly, at this point, again from infinity, goes to 0 at 3 pi by 2 and again approaches negative infinity. Similarly, from infinity, goes to 0, approaches infinity, negative infinity, and so forth. The domain of this function clearly is all real numbers except n pi, where n is natural number. The graph never attains any value at n times pi. That is 0 pi, 1 pi, 2 pi, negative 2 pi, etc. This is tan x. This is cot x. Next comes is the secant x and the cosecant x. For the function secant and cosecant x, we'll need the graph of sin x and the cos x. We do the following. So I'll be drawing on the sin x and the cos x function with red pens. Secant x is reciprocal of cosecant x. So we first make the graph of cos with dotted lines like this. Now we draw parabolas over where cos attains its maximum from both sides. These are graph of secant x. So essentially, secant x never touches the 2n plus 1 pi by 2 terms from any side. It starts approaching infinity from those sides. Like this. So for secant x, the domain is R minus all the terms of 2n plus 1 pi by 2, where n is a natural number. While the range, as you can clearly see, is from negative infinity to negative 1 closed union 1 to infinity. We do something similar for sin x. For sin x, I shall use violet pens. We draw the graph of sin x, and wherever the sin x approaches to its highest point from bottom and from the top, we start making parabolas. This makes the graph of cosecant x. Clearly, it does not touch the points of n pi. Meaning it approaches infinity at points of n pi. So, the domain of cosecant x is all points r minus n pi such that n is natural, while the range of f is again minus infinity, comma minus 1, union 1, comma infinity. The range of cotangent function is again minus infinity, comma infinity. Next comes an important section of functions known as the logarithmic function. A function f of x equals log to the base x, where a is a positive constant, is known as the logarithmic function. The function looks something like this on the Cartesian plane. You have something approaching from the left hand side from negative infinity, goes to 0 at x equals 1, and then starts increasing to positive infinity. Notice that log of 1 to any base a is always 0. Log of 0 to any base a is never defined. Clearly, as you change the base, the speed of the graph changes. For instance, if this is log x, if this current graph is log x, then log to the base 2x would look something like this. something like this. Basically, it would move faster, is what I mean. If you have something like half log x, then the graph would move slower. Something like this. And so on and so forth. We'll learn about this more in the transformation of functions. Now comes to transformation of functions. So we have the following transformation of function rules. We just need to follow the rule and any function can be shifted from its particular domain. So we have a transformation of function, that is, if we have c greater than 0, then you give a c unit upward shift for f of x plus c. You give c units downward shift for f of x minus c. You give c units to the left for f of x plus c, while you give c units to the right for f of x minus c. Next comes to stretch and skew a graph. So for c times f of x, where c is greater than 1, we stretch the graph by a vertical factor of c. For 1 over c times f of x, we shrink the graph by a vertical factor of c. Again, for f of c times x, we shrink the graph horizontally by a factor of c, while for x by c, we stretch the graph horizontally by a factor of c. Next comes flipping over the x or the y axis. So for negative f of x, we flip the graph about x axis, while negative f of negative x, we flip the graph about the y axis. I'll suggest you to go through your homework problems to work on these problems even more. We now come to an important topic known as combination of functions. For a function f and g, where a is the domain of f, c is the codomain, b is the domain of g, d is the codomain, we have f plus g of x to be f of x plus g of x, f minus g of x to be f of x minus g of x, f times g of x equals f of x times g of x, while f divided by g of x equals f of x divided by g of x, given g of x is non-zero. Consider a note about the domain. The domain of f was a, while the domain of g was b. Then the domain of f plus g is a intersection b. F minus g is again a intersection b. Same goes for f times g, which is again a intersection b. While for the division function, we look at the following. X belongs to a intersection b, where g of x is non-zero. Next comes the composition of functions. You have a function in the following fashion. You have a function from d to e and then to f. So g is a function from d to e, while f is a function from e to f. Then we define the function in the following manner. We have the first function to be g of x. And then we have the second function f of g of x. Therefore, this function is written as fog of x or fog of x. The second kind of function, where the first function is f while the second function is g, then we write in the following manner. We have the first function is f of x. The second function is g of f of x. So we have gof of x or gof of x. Clearly, we have to take care of the domain and the codomain of the first function to determine the domain and the codomain of the second function. We'll understand that by an example. Consider f of x equals x squared, while g of x equals square root x minus 1. We calculate FOG, FOF, GOG, GOF. First one is f of g of x. So look at f of, what is g of x? Square root x minus 1. What is f of square root x minus 1? We plug in square root x minus 1 in f of x. So we get square root x minus 1 squared, which is x minus 1. Now we look at g of f of x. We look at g of what is f of x? X squared. Now we look at g of x squared, which is square root of x squared minus 1. Next we look at f of x. That is f of, what is f of x? X squared. What is f of x squared? We plug in x squared in the function f of x. So we get x squared the whole squared, which is x raised to power 4. Now we calculate g of x. We have g of, what is g of x? Square root x minus 1. Now we have g of square root of x minus 1. So we again plug in square root of x minus 1 in g of x. Then we have square root x minus 1 minus 1. So we have square root x minus 1 minus 1. Looking at these functions, you might want to calculate the domain of these functions. So calculating the domain and range of composite functions, you do not have to do much. It's only using the previous methods. So we have f of x say equals x, and g of x say equals, f of x considered to be x cube, while g of x to be say like x squared minus 5. What we do is we want to calculate the domain and range of FOG and GOF. Let's first calculate what is FOG of x. FOG of x is f of g of x, which is essentially f of x square minus 5, which is x square minus 5 the whole cube. Expanding this, we have x raised to power 6 minus 125 minus 3x power 4 times 5 plus 3x square times 25, and this will give me x raised to power 6 minus 15x power 4 plus 75x square minus 125. Notice that this is a polynomial function. So clearly my domain is all real numbers. Now I look at the range. The range is also all real numbers. Next comes g of f of x, that is gof of x. So I have g of f of x. What is g of f of x? So g of, what is f of x? X cube. What is g of x cube? We plug in x cube in g of x. So we have x raised to power 3 square minus 5, which is x raised to power 6 minus 5. Clearly the domain is again real numbers because this is a polynomial function. The range is also real numbers. What I want to tell is that to calculate the domain and range of FOG and GOF, we just need to first calculate what is FOG and GOF and then use our usual rules to find out the domain and the range. Next comes the concept of increasing and decreasing function. So let f be a function on an interval to real numbers. Then a function is said to be increasing if for x1 less than x2 we have f of x1 less than f of x2. That is, as x increases, f of x will also increase. While a function is said to be decreasing for if x is less than x2, then f of x is greater than f of x2. That is, as x increases, f of x shall decrease. Let's look at this example of this graph. Clearly from the graph, you should be able to see that the function increases from a to b and c to d, while the function clearly decreases from b to c. So we write f of x increases from a to b and c to d, while decreases from b to c. Again, not every function can be categorized as increasing or decreasing function. We could have functions clearly which are half increasing or half decreasing, or nowhere increasing or nowhere decreasing, and so on and so forth. A function may not be categorized into these two forms. This ends our topic on catalog of functions. I would suggest you to do as many as problems possible from Stuart Calculus and from your homework. Thank you.